Hello, welcome to part 3 of our lecture on stars. In this part of the lecture, we will be looking at the birth and death of stars. So where and how are stars born? Well, it happens inside of these giant molecular clouds, and you can think of these as stellar nurseries. These are the birthplace of stars. This is a famous image of a giant molecular cloud taken by the Hubble Space Telescope. This image is called the Pillars of Creation, and it's a section of the Eagle Nebula. And remember, a nebula is a cloud of gas and dust in space. So you can see the details in this dense cloud of gas and dust. And within this cloud, new stars are forming. And we're going to look at that process in this chapter and learn how this happens. So these giant molecular clouds are mostly hydrogen, made of hydrogen. In fact, instead of atomic hydrogen, it's actually molecular hydrogen, H2. And you can see the size of these clouds can be enormous. They can range anywhere from 50 to 200 light years in diameter. And remember, a light year is almost 6 trillion miles. Also, these clouds are extremely cold. They're only about 10 kelvins above absolute zero. The other thing about these clouds that's significant is there's a lot of material in this cloud to make new stars. In fact, the mass of these giant molecular clouds can vary from 100 up to 1,000,000 solar masses. So there's enough raw material in these clouds to make not just one star, but to make thousands of stars. This slide here is one of the key slides of this part of the lecture because it describes the stellar life cycle. We can think of stars almost as if they were alive, in that they are born, they grow, they evolve, they change as they age, they get old, and eventually they die. And when they die, they return all of their material back to the universe for the next generation of stars. So it's very similar to a biological life cycle. So let's take a look at these steps. So we can start up here. So new stars are born from the gravitational contraction of gas and dust clouds, forming new star clusters. So this is another one of those nebula that contains gas and dust, and inside the nebula, the gas clouds are contracting by their own weight due to gravity and forming new stars. And stars are born in batches, not just individual stars, but hundreds or even thousands of stars are all born together. And this is an example here of a star cluster of relatively young stars that have emerged from a nebula like this. So these stars then live out their lives fusing hydrogen into helium for energy, just like our sun. And also other heavy elements are formed by nuclear fusion inside their cores. So these stars in this cluster will eventually go their own ways and separate and spread out across our galaxy. At the end of a star's life, it runs out of fuel. Basically, it runs out of hydrogen fuel and some of the other lighter elements that can be used for nuclear fusion. When this happens, the star dies. And we'll learn about how the stars die later in this lecture, but the most massive stars die by a violent death called a supernova explosion. And this means the entire star blows itself apart. And this picture here is what's called a supernova remnant. It's what's left of a star that blew itself up. But the key thing about this death of the star is that it's returning all of its material back to the universe for the next generation of stars to come from it. So this cycle is definitely cyclic, and it goes around and around and around, and it turns out our sun is probably a third or fourth generation star. So let's look at this process in a little more detail. So I mentioned earlier that stars are not born individually, but they're born in batches called a cluster, a star cluster. So a giant molecular gas cloud which, remember, has a total mass of hundreds to millions of suns. And within the giant molecular cloud, as is shown here, there is a non-uniform density. So there are certain regions inside the cloud where the gas and dust is thicker than other regions. So you can kind of see this. This is just a drawing or a sketch of what's going on here. But these dense areas within this giant molecular cloud have stronger gravity because there's more matter there, there's more mass. So they act like a seed for gravitational collapse. So the result is this thing now is going to start, each of these little pockets of dense gas and dust is starting to contract and pull in more gas and dust and fragmenting into pieces. So the result is fragmenting or fragmentation, and each of these fragments within this giant molecular gas cloud is going to form a protostar, which will eventually become a star. So you can kind of see how it goes in stages here. These thicker regions in the gas cloud actually become stars. So the pre-birth state of a new star is called a protostar, and it's not quite yet a star in that it's not producing its own energy yet. It's not shining bright like it will later on after it's born, basically. So this is sort of like the embryonic stage of a star. And the reason it's not shining yet is because it hasn't contracted quite enough to get hot enough. It needs a temperature of roughly 5 million degrees inside the core of this protostar to ignite nuclear fusion. So until that happens, this thing is just sort of glowing in the infrared. It's giving off heat, and that's why this is an infrared image to actually see this protostar. Star formation is very common in our galaxy. There are hundreds of places in the Milky Way galaxy alone where we can actually observe star formation in various stages. And by looking at all the various stages of star formation, astronomers have been able to put together a very nice sequence of steps of how stars are formed. So I'm going to share with you just a few images here of star formation region. This is called the Cone Nebula. And this, you can see in this nebula, first of all, you can see a lot of the hydrogen gas, which glows, remember it glows pink in color, and you can see dust clouds within this too. And remember that this cloud here is enormous. Our solar system, with all of its planets, would be a little speck in this picture here. You would need a microscope to see it. So that gives you an idea of the extent and size of this gas cloud. So within this nebula, the Cone Nebula, there are multiple stars that have already been born and more are forming. So you can see these real hot blue stars. Remember that blue in astronomy tells us that the star is hot. And also, we know that hot stars don't live very long. Blue stars only live about 1 million years. So these stars in this picture, these real bright ones, these are relatively young stars that have just formed in the last few millions of years, which, you know, sounds like a long time ago to us, but remember, in cosmic time, 1 million years is just like yesterday. So these are newborn stars, these bright ones here. And then within the Cone Nebula here, there are more stars that are still in the process of forming. Here's another image of a star forming region, and again, you know, you can see the telltale markers are, we see the gas and dust cloud here with the nebula. This is the raw material from which stars are forming, and we also see some new blue stars that tell us that some of these stars that are newborn and they're relatively young in terms of cosmic time, and so these stars are the ones that have been born out of this nebula. Here's just another Hubble Space Telescope image of a star-forming region. Again, you can see the clouds of thick gas and dust, and then within the cloud you can see a cluster of new stars that are forming or already been recently born, and then within the gas cloud are other stars that are in the process of forming. I showed you something like this picture a little bit earlier in a previous chapter. These are pictures taken from the Orion Nebula, and what they found here is that the vast majority, almost all of the stars that are forming inside the Orion Nebula are surrounded by gas and dust disks. So they call these protoplanetary disks. Remember that planets form in these disks around the star. And you can see the star in the center of all of these. And so these are new forming stars, and around them we think will be future solar systems, perhaps just like our own. So the message here is that star formation is very common. It's seen. We have a lot of data and evidence, and astronomers study it in great detail. And also the other message is that we now know that planets also seem to form whenever stars form, and so that is good news for the prospect of finding life on other planets, because it appears that there are many, many planets in our galaxy. So when a human is born, it really doesn't matter what your birth weight is, as long as you're in a healthy range of birth weight. And how much you weigh at birth really doesn't factor in how you'll spend the rest of your life, right? You have free will and choice, and you can decide what you want to study in college or what job you want to have and so forth. It's very different with stars. A star's fate is completely determined and sealed as soon as it's born, and it all depends on the star's mass. So in other words, its birth weight determines the outcome and the complete life of a star. So let's just look at the two extremes. For the highest mass stars, so these are the stars that are born big, they are going to have more gravity squeezing their cores, which means they have hotter cores. This speeds up the rate of nuclear fusion, which produces more energy. So these stars have brighter, hotter surfaces. So this is an example, just this blazing bright blue star. Remember that blue means very hot. So this star is big, it's bright, and it's hot. This also means that this star is not going to live long. Remember that bigger stars die younger because they burn up their fuel faster. Now, on the other extreme, the stars that are born with a low mass, and it turns out that the vast majority of stars are born with a very small mass to them compared to even our sun. So they are going to have a much cooler core because there's less gravity squeezing that core down. Therefore, their rate of fusion is slower, making them less luminous, meaning not as bright. And they are going to have a cooler surface. That's why we see them as red in color. And because they burn their fuel so slowly and efficiently, they are going to have long lives due to this slow rate of fuel consumption. So whether the star, burns bright and hot and dies young, like up here, or whether the star is cool and dim and lasts a long time, it just depends on how big the star was when it formed. So now that we have an idea of how stars are formed and are born, let's take a look at how stars die. And this is very interesting. So first of all, what makes a star die? Why can't it live forever? Well, the reason is that stars, they basically run out of nuclear fuel. So you can think of a star, again, kind of like an automobile with a gas tank. And as soon as the gas tank runs out, the car doesn't work anymore. So stars are in a way like that. When they run out of hydrogen fuel, they basically are running out of energy. And so what happens then is gravity takes over and crushes the star. So the smallest stars actually die a very peaceful death, but the largest stars explode violently. And this animation here is showing what a supernova explosion looks like when a massive star comes to the end of its life and blows itself up. As I talked about a couple slides ago, the mass of a star when it's born determines basically how the star will live and how it will die. So this slide here is sort of a summary of what can happen to a star when it dies. So the smallest stars, which are less than about 0.4 times the mass of our sun. Remember this M with a little symbol here? This symbol means our sun. So this is M, this is a solar mass, okay? So stars less than about 40% of the mass of our sun become a white dwarf. And this is a very peaceful transition. The star, and we'll kind of talk about this in a little more detail soon, but the star basically runs out of fuel and gravity just sort of squeezes it down into this little compact remnant of what it used to be. It still has a lot of mass, but it has hardly any size. It's about the size of our Earth. And this is called a white dwarf. For stars like our sun, typically about 40% up to maybe 8 times the mass of our sun. What happens when these stars die, when they start to run out of fuel, they swell up basically first, and they become a giant star. And remember, we talked about these in the HR diagram. There's a whole population of giant stars above the main sequence on the HR diagram. And then after the giant star, the core of the star, the central part at least, will shrink down and again become a white dwarf, like as is shown over here. So this is again, a fairly peaceful death, although there is this swelling phase here that we'll talk about soon. Now let's look at the medium mass stars. Stars around 8 to 20 solar masses. So these are stars about 8 to 20 times as massive as our sun. They swell up into a giant star, but then they explode, and they explode in a supernova explosion, which is one of the most violent explosions in the universe. And after that, the core of the star actually survives. The outer layers of the star all explode outward, as is shown in this image here, but the core of the star shrinks down into a very strange and exotic object called a neutron star. And we're going to study neutron stars in part 4 of this lecture. Finally, the biggest stars, stars bigger than about 20 times the mass of our sun, they become a giant star, a supernova, but then their core keeps shrinking and shrinking and shrinking until it basically disappears. And this forms one of the most mysterious and fascinating objects in the universe. This is called a black hole. And a black hole is something we will also be talking about in more detail in part 4 of this lecture. So let's look at a couple of these death processes in a little more detail. So we said that stars smaller than the sun quietly die. And basically what happens here is inside the star, we have a mixture of hydrogen and helium. And remember, the star is fusing hydrogen into helium inside the core here. All right, so the hydrogen is being transformed by fusion into helium. But this small star, there's mixing and churning going on here. So there's basically, as long as there's some hydrogen left inside the star here, the star can still shine. But once the star uses up all of that hydrogen, the star becomes completely filled with helium, and the star is not hot enough to fuse helium. So basically at this stage it's run out of fuel. So what happens now is this star can't produce energy anymore. There's no more nuclear fusion, so it can't hold off gravity. So gravity just starts to squeeze this star down and compress it. This is a gravitational collapse, and it collapses down until it becomes a white dwarf, basically a solid ball of helium, roughly the size of the Earth or even smaller. For sun-like and larger stars, what happens is, first of all, when the star, like our sun, runs out of hydrogen inside of its core, so these little red dots in here represent hydrogen, they all turn into helium, right? They all fuse together to form helium. And what happens then is this core here contracts due to gravity. And when you compress or contract gas, it heats up. And so by heating up the core, a strange thing happens. The outer layers of the star start to expand, and they keep expanding outward until they become this bloated version of the original star, and this is called a red giant. So what happens here is the core is actually hotter than it was originally, but the outer part of the star, because it's expanded so much, is actually cooler than it was before. So it usually shifts over to the red part of the spectrum. So we can see on the HR diagram the pathway of stars as they expand off of the main sequence. So remember, here's our HR diagram. This is brightness here, and this is temperature down here. Remember, it's reverse order. This is hot over here and cooler stars here. So this red line here represents the main sequence. This is where stars live their life. But when stars die, they leave the main sequence. So for example, our sun, which is right here, right now, and will be for another 5 billion years, will eventually expand and swell up, and it'll move up and to the right on the HR diagram. It's cooling off, which means it's going to the right to cooler temperatures, but it's also moving up because it's expanding to be so big and it's so hot in the middle that it's giving off more energy, so it's actually brighter. So our sun will end up somewhere over here in the HR diagram. Other stars, you can see, will follow different pathways from the main sequence to where they eventually live. And there are some stars like these, Rigel and Betelgeuse, that are supergiant stars. These stars can be as much as 1,000 times the size of our sun. And you can see several other examples of giant stars here. Giant stars are very common in the universe. We can see them across our galaxy because they are so bright. So let's take a look at our sun specifically and see what its future is. So right now, our sun is happily and very stably living its life on the main sequence. So it will remain on the main sequence for a total of about 10 billion years. That's the lifetime, the lifespan of our sun. Since our sun is only about 4.5 billion years old, you can see that it's only roughly halfway through its life. So our sun is middle-aged. But in about 5 billion years or so, our sun is basically going to run out of fuel in its core. It's going to convert all of its hydrogen in the core into helium, and what's going to happen then is the core is going to shrink and heat up, and it's going to expand out the outer layers. So our sun will expand into a red giant star. It will become huge compared to where it is now, and we'll talk about that in a little more detail on the next slide. The next thing that will happen is inside the core, fusion will finally stop. And what will happen then is the core will shrink down to become a white dwarf made out of carbon and oxygen. And then in the last sort of gasp of our sun's life, it's going to probably cast off its outer layers of atmosphere and form what's called a planetary nebula. And we'll talk about that later as well. But in the center, what remains is the little white dwarf. This is the little ember of what will be left of our sun once all of this gas dissipates into the universe. And so finally, at the very end of its life, our sun will just be a tiny little white dwarf star, and it'll basically be an ember that just cools off with time. It's no longer producing any energy here, so it's doomed to just cool down and cool away and fade away basically. So this is, again, talking about the fate of our sun and the end of Earth. Our sun, again, in about 5 billion years, it's going to expand in a red giant. So this is maybe what our sun will look like in the future on our Earth. So you can see our Earth is pretty much scorched here. It's been basically fried by the increased luminosity and brightness and size of the sun. And notice how big the sun looks. Here's the moon. So right now, the moon and the sun are about the same size in the sky. That's why we can have a solar eclipse. But in the future, this is a solar eclipse, but you can see that the moon looks tiny compared to the enormous swelled up size of the sun. So how big will the sun get? Well, we don't know for sure, but it'll almost certainly engulf Mercury and probably Venus and maybe even Earth and Mars will actually get swallowed up by this swollen sun. So it's not a happy ending for our planet Earth. Earth will become basically vaporized by our sun. The oceans and atmosphere will boil away first, and then the crust will itself boil and become incinerated. So don't get too depressed though, because we've got some time before this is going to happen. This is not going to happen for billions of years. What's going to be left then is our sun will probably produce a expanding shell of gas. This is an actual image here of this is called the Ring Nebula, and it's an expanding shell of gas that's cast off from the star that basically died. And you can see in the center here, that little white spot there is the white dwarf. That's what's left of this star. And this is these are really beautiful to see, these planetary nebula, they're called. It's just what's left of the outer layers of the star have been just shot out into space. And there are many examples of this in our galaxy. So our sun will probably do something like this in roughly 5 billion years. One way to think of the evolution here is, again, on the HR diagram. This is the main sequence. So here's our sun right now. It's sitting right here inside the main sequence. But in 5 billion years or so, it's going to move up here and become a red giant. And then the core of our sun will shrink down and become a white dwarf and do some path like this, or maybe like this, doesn't really matter. And it's going to end up down here where all the white dwarfs are. These are these tiny little remnants of stars that are left over. So since our sun is going to become a white dwarf, and in fact, all of the small sun-like kind of medium and small stars will become white dwarfs. Let's look at them just in a little more detail. A white dwarf is a compact, super dense stellar core remnant, meaning what's left of the star after it dies. And they're made of helium, carbon, and or oxygen. And just to get an idea of its size, so here's our sun in the background here, this big yellow ball. There's our tiny little Earth, right? Well, look at the white dwarf is roughly the size of our Earth. So our sun is going to eventually shrink down to something the size of our Earth, and that will be its final resting state. But it'll have all of the mass of the sun, something like 300,000 times the mass of the Earth, all crammed into this little white dwarf. So white dwarf material is very exotic. There's nothing like it on Earth. We can't, make white dwarf material. It's actually called degenerate matter by physicists. But 1 teaspoon of white dwarf material would have the mass of something like 16 tons. So imagine taking, for example, 10 cars or trucks and smashing it down smaller and smaller and smaller until they all fit inside of a spoon. Right? This is what white dwarf material is. It's very strange material. Another kind of fascinating concept, and we don't really know if this is true or not, but it's been speculated by scientists that carbon white dwarfs, all right? So remember this ball here that's the size of the Earth is basically super dense liquefied carbon, and once it cools down, it may crystallize and become basically a diamond. So they sometimes call these diamond stars. So imagine a diamond the size of our Earth, solid, one single diamond. I don't know how many carats that would be, but it would probably cost quite a few dollars if you tried to buy that for an engagement ring. One of the most amazing and important things about the way stars die is that they create heavy elements inside their cores. So stars are nuclear factories fusing light elements into heavier ones in a sequence of shells. And this is where all the elements come from. And so this is sort of an amazing creation story, one that's based on science. So if you think of the way a star works, inside the core of the star, hydrogen is fusing to helium. So this is what's happening inside of our sun right now. Our sun is fusing hydrogen into helium to produce its energy. Well, what happens is later that helium that has been produced can actually fuse into carbon. All right, if you take 3 heliums and fuse them together at high enough temperatures, like inside the core of this star, you get carbon. And carbon can fuse into oxygen. Oxygen can fuse into neon, which can fuse into silicon, etc., etc. So what we end up with is a sequence of layers, kind of like, layers of an onion. And the farther we go into this core of the star, the heavier and the heavier the elements become. So this is happening during the final stages of a massive star's life. So these are the really big stars. Stars that are bigger than our sun will create all of these elements. In fact, they create them all the way up to iron. Now, so this is, if we think about this, if we think of, just what's going on in our bodies, right? Our bodies are made of carbon and oxygen and iron, right? We have iron in our blood, calcium in our bones. All of these elements were produced inside of a star like this. Now, we're at the final stages of this star's life. Remember, we've got all these layers upon layers upon layers of heavier and heavier elements that are getting cooked up inside the core of the star. Well, once we get to iron inside the core here, it turns out that iron, because it has the highest nuclear binding energy, we can't squeeze any more energy out of it. The star can't use iron for fusion to get any more energy. So this is where the star has now run out of nuclear fuel. It has no options left. So what happens now is this whole core collapses because it can't produce energy to withhold, to fight off gravity. So gravity squeezes this core down in a tiny fraction of a second. So basically this core of the star implodes, right? It doesn't explode, it implodes. It explodes inward, and there's a recoil that blows up the entire star, and this is the supernova explosion. And the supernova explosion is basically like a giant nuclear bomb going off. And we're talking about not a nuclear bomb that could fit on a desk like a normal military nuclear weapon. We're talking about a nuclear bomb that is larger than the Earth, right? The core of this star. And so this thing, it has an enormous amount of nuclear fuel and material in it that explodes. So during this explosion, all of the elements in the periodic table are created through fusion reactions and neutron absorption, and there's all kinds of nuclear physics reactions going on that we're not going to talk about. But basically, the idea here is that while this star dies and explodes, it creates every single element in the periodic table. This is the creation and formation of the elements. So, if you ever wonder, where do all the elements come from? When you look at a periodic table, you see all these different elements: gold, platinum, silver, tantalum, titanium, sodium, just you can keep naming, right? There's over 100 elements here. Where do they all come from? Well, they all came from a star. So the death of a massive star by supernova is one of the most amazing things in the universe because of the amount of energy it releases. In fact, when a star goes supernova, it can outshine its entire galaxy. So think about that. In a typical galaxy, there are several hundred billion stars, just like our sun, all shining brightly. But when a supernova explosion happens, that explosion, it outshines all of those hundreds of billions of stars. So they're very easy to observe. We can see them across the universe. And they happen about once per century in a galaxy. Okay, so, but fortunately there are so many galaxies to observe that many supernovae have been observed. So here's a sampling of some actual images. So this is a spiral galaxy here, and this bright object right here is a supernova explosion. It's one of the hundreds of billions of stars in this galaxy that blew up. And the brightness of this one star is as bright as the entire galaxy combined. Here's another one here. This bright object right here is a supernova explosion associated with this spiral galaxy here. These other stars that you see in the picture here, those are foreground stars in our own Milky Way. So we're looking out of our Milky Way to see these distant galaxies. Here's another spiral galaxy here, and this star right here is a supernova explosion. And here's one last example here, another spiral galaxy, and here is the supernova explosion right there. I was fortunate enough to be able to actually go and photograph a supernova explosion. Back in 2011, there was a supernova reported in the galaxy M101. And so I took my telescope and camera up to Laguna Mountain and got a picture of it. So this fuzzy thing in the background here, this is the galaxy M101. It's also called the pinwheel galaxy, which you can kind of see why. It's a spiral galaxy with these spiral arms. Now remember, what this galaxy is, it's a collection of several hundred billion individual stars. Now remember that these bright stars that you see in this picture here are not part of this galaxy in the background. They are part of our own Milky Way. So you can see, if this was in 3 dimensions, these stars would be very close to us, and this galaxy is very far away. So this is the actual supernova right here. That bright blip should not be there, and it wasn't a few days before this until somebody discovered it. Now here's what's kind of amazing about this. First of all, this picture is not the greatest, but this galaxy is far away. It's 27 million light years away. But think about what that means on the timing of this supernova. So the question is, all right, I took this picture in 2011. So when did this star actually blow itself up? Well, it wasn't in 2011. It was a long time ago. Now, how long ago was it? Hint, right here. Remember, it takes light 1 year to travel a light year. That's the definition of a light year. So this galaxy being 27 million light years away, that means that this supernova actually blew up 27 million years ago. And we just got to see it recently. So again, this is one of those kind of profound things when you think about astronomy. What we're looking at when we look through our telescopes is we're looking into the past. And the farther out in space we go, the farther back in time we're looking. So in a sense, my telescope, like anyone's telescope, is a time machine. And it allows us to look back in time. This is our last slide here on this part of the lecture, and this is another really fascinating example of a supernova remnant, the remains of an exploded star. So this is an actual image taken of what is called the Crab Nebula, and the Crab Nebula is what's left of a star that blew up about 1,000 years ago. And what's amazing about this is that this star, when it went supernova, it was observed and recorded by Chinese astronomers. This is in the year 1054 AD. But also, more at home here, it was recorded by Native Americans in Chaco Canyon, New Mexico. So there is a cave and an old archaeology site now of a dwelling where the Anasazi used to live. And on the ceiling of this cave is this famous painting now, and it depicts a star here, a bright star in the sky next to the crescent moon. And this is precisely where this supernova was when it exploded in comparison to the phase of the moon and the position of the moon in the sky. So whoever saw this back then, or one of our Native Americans saw this and actually recorded this with a painting, and we think this could be the artist's signature, his hand painted on the ceiling of the cave as well. So this is one of my favorite kind of links between astronomy and our ancestors, basically. Okay, that is it for part 3 of this lecture. We got to see how stars are born and die. We will continue on with the last part 4 of this lecture next. I will see you then.